Good morning. We have been spending the last 4 lectures looking at moment distribution, and I had promised that today I would take up a problem which would include sway. And last time we looked at a problem where the only load that was applied was the sway load, and therefore computation of the no sway reaction was relatively simple. This time we will show you we'll take up a problem which will deal with the entire spectrum of issues that you have in using moment distribution for a frame problem which has sway degrees of freedom. So let us take one of the old problems that we've already looked at using the method displacement method, and this was the problem that we had looked at a long time ago, and I'm just going to redo this problem. The advantage of this is that if we use the moment distribution method, we already know the answer to this problem when we have used the displacement method. And therefore, if the moment distribution method gives you the same result, it gives you confidence that the moment distribution method actually does solve the problem in a similar manner. Okay, so this is your essential problem. E is the same, material is the same. So this problem can actually be done in this fashion. If you remember, we had transferred that CE load as a 50 kilonewton load here, and by the way, this was 5 meters, so this is 250 kilonewton meter, and then you have all these other things. So this is the problem that I am going to be actually looking at. Okay, in this case, what's the first step? Well, you know that there are 3 degrees of freedom. These are the 2 rotations. There is a sway degree of freedom. So the first step is essentially to solve the problem, the no sway problem. So how does this problem look with no sway? You essentially have and to stop the sway, I put a support here so that this does not allow this. And essentially, we solve the entire problem to find out this R. Okay? So now, first things first is we need to write down the fixed end moments. And this we have already done earlier, so I am not going through the steps. We know that this is plus 22.2 kilonewton meter. Fixed end moment BA is equal to minus 44.4 kilonewton meter. Then fixed end moment BC is equal to plus 288 kilonewton meter. FEM CB is equal to minus 192 kilonewton meter. CD is equal to fixed end moment DC is equal to 0. And another point here, you have to include the fact that CE is equal to plus 250. The reason for this is that understand that although I have put the load here at this particular point, it is very important that to understand that the total joint reaction includes when you take the equilibrium of the joint, you will see that this 250 kilonewton meter, and note that I am putting it as plus 250 because this is actually a load applied here. I can consider it as a moment applied here, and so that would be the moment that I need to consider in the joint equilibrium. Okay, so that's the reason why I have this. It's different from the other concept. Okay, so the only thing is that CE will not take any this thing. It is not a member which takes any part in the stiffness. So when we compute the relative stiffnesses, if we look at it, KAB, AB is a normal member, so KAB is going to be I upon 15. KBA is equal to I upon 15. KBC, if you look at BC, it's 4, see I1, I1, and if we look at it, that KBC, we saw that the moment of inertia of BC was 4 times I. So we have 4 times I1 upon the total length, which is 20. KCB is similarly 4I1 upon 20. Okay. KCD is I1 upon 15. KDC is I1 upon 15. And note that Kc is equal to 0 because it's a cantilever. Okay. So therefore, this is included in the computation at C. Okay. So there are two distributions that we have to do, that is at distribution at B and distribution at C, and therefore dBA, you can see, is going to be equal to I upon, so it's going to be 0.25. KBA is I1 upon 15, and here we have I1 upon 15 plus I1 upon 5. So dBA becomes 0.250 and dBC becomes I1 upon 5 upon I1 upon 15 plus I1 upon 5, which is 0.750, and at joint C we have dCB is equal to 0.750, dCD is equal to 0.250, and dCE is equal to 0. Okay, so these are the distribution factors. Carryover factor, this is a normal problem, so carryover factor has half from each side, excepting that when you have carryover from A to B is 0 because A is a fixed end, and carryover from D to C is 0 because D is a fixed end. Okay, between from B to A, carryover is half. From B to C as well as from C to B is half, and carryover from C to D is half. These are standard things. So once we've done that, we can now put together the no sway problem. Okay, so if we look at the no sway problem, let me put it down in this fashion. Again, being consistent over here, you will see that (1.0). Again, this one is over here, 1.0. Okay. Then we have over here, this is for BA, so the distribution factor is 0.25. For the BC, this is this, so this is 0.75. Here, again, this one is for CB, so it's 0.75. This is for CD, and ultimately I'm going to put this for CE, but this is going to be 0.0. The only thing is that here we have plus 250. Okay, what do we have here? We have plus 22.2. Here we have minus 44.4. Here we have plus 288. Here we have minus 192. Here we have 0. Okay, and here also we have 0. So I've written down all the fixed end moments, I've written down all the distributed factors. So now what I'm going to do is, I'm going to do this in this fashion, that I'm going to do the distribution at both joint B and C. So if you look at this, there's a plus 243.6 there's a plus 243.6. So we have to do a negative 243.6 and distribute it. So that's going to become equal to 182.7, and this is going to be minus 60.9. Okay, so this distribution is over. So done here. Do the distribution over here. We get 250 minus 192. So that's going to be 58, and 58 has to be distributed. If we distribute 58 in 3 by 4, we get minus 43.5. This thing is plus 58, so minus 58 has to be distributed, and this is going to be minus 14.5. And this is 0. Distribution done. Put it here. Now the carryover from here to here is going to be minus 91.4. Carryover from here to here is going to be minus 30.5. Carryover from here to here is going to be minus 21.8, minus 21.8. Carryover from here to here is going to be minus 7.3. Okay, so we've done all the carryover. Now again we do the distribution, and so I'm not going to spend too much time on this. I'm just going to put down the values, and you know what the values are going to be. This is done, so I can put then I do this over here. It's going to be minus 91 distributed is going to be plus 68.6 and plus 22.8. So here we'll have plus 11.4. Then here we will have 30 I'm sorry, this is distributed. So it's going to be plus 34.3. That's the carryover here. Carryover over here is going to be plus 8.2. We've already done the carryover here, and the final carryover of this to here is going to be plus 2.8. Okay, next we again do this. This is going to be plus minus 8.6, then minus 25.7. Close this. Okay, and that is here. This one needs to be done, so this is going to be minus 6.1. Close. This is also closed. This is 0. This is going to be minus 2.1. Close. 0. Okay, and ultimately, so you can keep doing this. I'm not going to go any further. You know the steps. I'm going to write down the ultimate value that you're going to have at this point. At this point, you're going to have minus 108.8 at this end. Here you're going to have plus 108.8. Here you're going to have minus 9.4. Here you're going to have minus 259.1. Here you're going to have plus 9.1. Here you're going to have plus 250. And here you're going to have plus 4.6. So these are the final moments that you get after. When do you stop? You stop when your distribution gets to be less than 1% of the smallest value. Which is the smallest value over here? It's 280, highest value 288. So 1% would be about 2.8. And as soon as your carryover becomes less than 2.8, you stop the entire process. Always end the last process in a moment distribution should always be the distribution. It's just that you do not do carryover, which is less than 2.8 here in this particular case. Okay, so once we have these moments, so now what's the next step? Next step is, well, actually you put it down on a figure. So what you have is for each one, you know the member and moment. The member and moment minus means it's going to be this way. So it's going to be 9.4. On this side, it's going to be clockwise. So it's going to be 108.8. These are kilonewton meter. I'm not writing them down. Okay, and here you have 20 kilonewton meter. So understand that for this, I can find out the force over here. So if I look at this particular force, what do I get over here? If you take this moment and you subtract this aspect of it, you're going to get that this force, this is this way, so this will be this way. So it's going to be in this direction, and this is my horizontal at A. Okay, and similarly I need to find out at D. We put it all together. This is going to be 100. This is going to have 108.8. Here this is going to be 259.1. Here this is going to be plus 9.1, this is going to be plus 4.6, okay, and understand that here you have this, and here you have a net moment of 250, so that they balance each other out. Here these balance each other out automatically. So all we are interested in is actually finding out how much this, so this is going to be H at D. H at D, so let us calculate what H upon A, HA is going to be. HA is going to have two components. One component coming from the moment, that's going to be equal to, that's this way, so it will be this way, so it's positive, so it will be 108.8 plus 9.4 divided by 15, okay, and then you have the other load is in the other direction, and that is equal to 20 into 5 by 15. So if you look at this, this turns out to be equal to 1.21 kilonewton. Let us look at HD. HD, this, we're going to have this. So HD is going to be equal to 9.1 plus 4.6 upon 15. So this is going to be equal to 0.91. And understand that if I look at this, so that means if I look at the entire structure, okay, if you look at the entire structure, HA, HD, HA is equal to 1.21, HD equals 0.91, okay, and we have a R reaction here, okay, and you have load 20 kilonewton here, okay. So if you look at that R and you take, this is going to be R plus 20 plus 1.21 plus 0.91 is equal, minus 0.91 is equal to 0. This implies R is equal to minus 20.3 kilonewton. In other words, the loading, the reaction is in this. If you look at that, what does that essentially mean? That means that actually the structure wants to sway in this direction and you are restraining it, and therefore you generate a 20.3 kilonewton force. So R is equal to 20.3 kilonewton force in this direction. Okay, so that is something that we have done. So if R was 0, remember I had said that if R was 0, then you would know that there is no sway. But here you have R in this direction, which essentially means that the structure is trying to move in this direction. So essentially, the sway case, you have to consider the structure to be moving in this direction. So let us see what happens. So now I'm going to, this is swaying in this direction, so let us make it sway in that direction. You will see that this joint will go here, this joint will go here, and all you have is this, and the other part remains straight because it's a cantilever. Okay? So if you look at this, if we say this is delta and this is delta, what do we get? We get that the fixed end moment A, B, C, D. Fixed end moment AB is equal to, if you look at it, it's going to be plus 6 EI delta upon 15 squared, which is equal to FEM BA. You will see that is equal to FEM CD also, which is equal to FEM DC. All of them have this. FEM BC is equal to FEM CB is equal to 0. Okay? So, having done that, we can now say that the fixed end moment, this, let us say that this is equal to 100. Okay? So, if we say this is equal to 100, then we can say that the, say, 6 EI delta upon 15 squared is equal to 100 kilonewton meter. So, this is, we are assuming it equal to 100. We will find out what it actually is a little bit later, because we don't know what the delta is, and therefore we will find out the 100 what this is, the actual value of this a little bit later. So that's why I'm saying that when you look at the sway problem, what do you actually do? You put it equal to 100, so any one of them to be 100, and you can compute all other fixed end moments automatically. In this particular case, you will see that since all the moments are equal to 100, so we will get that all fixed end moments are equal to 100. That is that's incidental in this particular case. Okay. So now next step is to find out the your. So distribution factors remain the same. Distribution factors are what they are originally. So I am going to just now put now here 1.0, 1.0, 0.25, 0.75, 0.75, 0.25, 0. Here what is it? FEM AB is plus 100, plus 100, 0, 0, plus 100, 0, plus 100. So this is our starting, and ultimately if you look at it, the first step, this is minus, so you will have minus 25 minus 75. Here you will have minus 75 minus 25. That is distributed, and next 0 of course. Next minus 38 minus 38. This is a carryover from here to here. From here to here minus 13. From here to here minus 13. Okay, so we are done with the carryover. Now again we just have this. So this is going to be 1/4. So this is going to be plus 9.5, and this is going to be plus 28.5. This is going to be again plus 28.5 and plus 9.50. Carryover plus 4.8 plus 4.8, and here carryover is going to be plus 14.3 plus 14.3. Keep doing this, what's going to happen? Okay, ultimately you're going to be doing the same process. This one needs to be distributed. I am just all the steps. I'm assuming that you will be doing all the steps. So you continue with the steps. It's not ended here. Okay, so you're going to have continuous steps here. These are going to be 0. So ultimately I'm putting down the final value. The final value over here is going to be plus 81.8. This is going to be minus 81.8. This is going to be equal to plus 89.9. This is going to be this is going to be minus 81.8. Note that it's symmetric, so you're going to have exactly the same anti-symmetric. So you're going to have the same values coming through. This is going to be plus 89.9 and this is going to be 0. So we've done the moment distribution. Okay, I've not gone through all the steps. Again, where do you stop? You stop when you reach when the carryover is less than 1% of the largest original fixed end moment. Largest original fixed end moment was 100, and therefore as soon as the carryover becomes less than 1, you stop the process. Okay, and these are the final. I'm just putting down the final ones that we have. Okay, so now if you look at it, what does this mean? So now, having got these, we need to find out what is the moment that we get over here. Okay, and if we put that in again, okay, we are essentially saying what kind of R1, okay, here this is like a load R1 which would give us this. So this R1 we need to find out, and that R1, how do we find out? We actually put down the values that we get here. So this is going to be equal to plus 89.9 81.8. Here this is going to be 81.8. This is 81.8. 81.8. 89.9. Okay, and if we put these in, this one turns out to be equal to 89.9 plus 81.8 divided by 15, which turns out to be 11.45. Similarly here we get 11.45. So if you look at the entire structure, which is this, and we know that the reaction here and here, and this is R1, you will see that R1 is equal to 22.9. So the main thing is, if R1 was equal to 22.9, okay, if R1 was equal to 22.9, then the moments over here that you would have was equal to 0. But understand that we got our reaction at that particular point to be equal to 20.3. So essentially, really, R1 is equal to 20.3, because when you put the two of them together, that's the actual load that you have at that particular point, which is equal to 0. Okay, so R1 should really be 22. So that means the sway moments, all the sway moments, okay, all sway moments have to be factored by 20 by 3 upon 22.9. So therefore, if you look at the sway moments, okay, if you look at the sway moments, they turn out to be equal to MAB. It's actually given as 89.9. In reality, it is this. MBA is equal to 81.8 into 22. MBC is equal to minus 81 into 20.3 upon 22.9, which is also equal to MCB. And MAB, you will see, is equal to MDC, and MBA is equal to MCD. So when you add these with the non-sway moments, okay, the final moments, if you look at it, what do they turn out to be equal to? You will see that you will get MAB. When you include both the sway and non-sway, the non-sway was equal to minus 9.4 plus is going to be equal to MBA is going to be equal to minus 108.8 plus 81.20. So this is equal to MBC similarly is equal to plus 36. MCB, if you add them up, you get it equal to minus 331.6. 259 and plus, okay. So CD is equal to 81. It's equal to 9.1 plus 81.8, 22.3 is equal to plus 81.6, and MDC is equal to plus 84.3. Okay, so once we have these, then my final member end moment, if you look at it, turns out to be so this is the final actual structure that I am going to put down. 50. So here we have 250 kilonewton per meter and 50 kilonewton shear. So you'll get just the opposite on that side. Okay. If you look at this, let us go through the entire thing. This one is like plus 70.3, so it's going to be 70.3. This is going to be minus, so it is 36.3. I have this load here, which is 20 kilonewton meter. Okay, if I look at this and I add the two up, I get 8.94. This is kilonewton meter, kilonewton meter, kilonewton meter. On this one, I get plus 84.3, and I also get this to be 81.6 kilonewton meter. So if you really look at it, 160 divided by 15, you get 165.9 divided by 16, you get it equal to 11.06 kilonewton meter. Okay, and over here you will get this equal to 11.06. Over here you will get 11.06. Okay, so if you really look at it, let's just go through the steps. This will be like this. Okay, and the moment will be like this. What do we have on this one? You will see that I have 100 kilonewton force acting over here. So if and what are the moments? MBC is plus 36.3, so it's 36.3. Then here this is minus 331, so it's going to be this way, 331.6. Okay, and if you really look at it, so I've got the moments down, and if I take, let's go through the procedure. Here, this one is going to be acting in this direction. This one is going to be acting in this direction. So over here you'll have this, and you'll have this. So over here you'll have this. So over here you'll have this. You'll have this. Okay. Sorry, over here you'll have this. So over here, just the opposite. And if you look at it, this plus this 11.6 will give you net Fx equal to 0, which stands to reason. If you look at this one, there's going to be this way, there's going to be this way. Just check it out. Okay, this is 331, this is 50. Okay, this is 250, sorry, 250 and 81.6. 250 plus 81.6 is 321.6, which is balanced. So there's moment balance, there's Fx balance. Now all we have to do is do Fy balance. So if you really look at this, this particular one, you have a net moment in this direction. So this is going to give rise to a force in this direction. So that's going to be equal to 331.6 minus 36. So 331.6 minus 36. This divided by 20. Okay, this is going to be a force in this direction. So if I'm taking force in this direction, this is this way, plus I have minus 100 into 12 upon 20. Okay, so this is my net moment which I get, and if you look at this, the net force over here is going to be equal to, in this direction, and it's going to be equal to, compute it. Okay, so once you get this is going to be this, now you can get this one is going to be equal to this is your VBC, and your VCB is going to be equal to 100 minus VBC. So you can compute this, and you will see that they all balance each other out. Okay, and ultimately, if I were to look at the support reactions, if you look at this is going to be equal to 60, and this one, if you look at it, is going to be equal to 2. Sorry, let me do this over here. This is going to be equal to 4.7. So this is going to be 295.3 295.3 upon 20, this is 60, so this is going to be equal to 60 upon, here you have 14.8, so 14.8, 60 is going to be equal to, upwards is going to be equal to 45.6, so this is going to be equal to upwards 54.4. So over here, what you have, support reaction 45.6 kilonewtons. Reaction here is going to be 8.94 kilonewtons. Moment is going to be equal to 70.3 kilonewtons. Over here, the moment is going to be 84.3 kilonewtons. This horizontal force is going to be 11.06, and the vertical force is going to be equal to 104.4 kilonewton meter. If you look at this, this balances everything out, okay? And ultimately, if you look at the total sigma fx equal to 0, you will see 8.94 plus 11.06 minus 20, it is checked. Sigma fy equal to 0, 45.6 plus 104 is going to be 104.4 is going to be 150, minus 100 minus 50, 0, check. And moment, take moment about A, and you will see that you will get it equal to 0, check. Okay, so this in essence finally tell you is that you have a situation in which you do have to solve a no sway moment distribution. By solving the no sway moment distribution, you get the no sway moments. From the no sway moments, you compute the horizontal reactions and you compute the total reaction required to ensure that there is no sway. Then the next step is to assume that there is sway and compute the load required to give you the sway that you get. Now that sway, that reaction, total sum of the two reactions have to be equal to 0, and because of that, when you put it all together, you finally get both, you add the sway and non-sway moments, you add the sway and non-sway moments, okay, these are the non-sway moments, these are the sway moments, corrected for the actual values, okay, and then once you get that, you've got the actual moments due to both the sway and actual structure. And ultimately, if you look at this solution that I have given to you is identical to the one that we computed due to using the displacement method. Okay, so essentially the moment distribution method, if applied using sway and non-sway distributions together, you will get the final solution. Now let me give you a particular problem. I will give you a specific problem and also give you the answers so that this you can actually compute what you're going to have. Okay, this is an old problem that we have looked at. It's just a little bit of a different loading that I'm putting on it. Okay, here I have 10 kilonewton and I have a UDL. Okay, this UDL is 4 kilonewton per meter length of bar. Okay, so here this is 2 EI, this is EI. Okay, this is 3 meters up to here. Okay, and here let me tell you that what you have to do is restrain this so that there is no sway, and this is the R that you consider for the no sway. Is that clear? In other words, for the no sway, you make this into a hinge. Okay, and I'll give you the final answers to this particular problem. When you solve it using the no sway case, you get R equal to 0.0854 kilonewtons. And it is minus, in other words, it's actually R equal to 0.0854 kilonewton going up. Okay, so okay, so therefore from when you do the no sway case, I'm going to give you the final answers that I have and find out if you can solve. If you can solve it, you know that you've done it correctly. You get 2.408 kilonewton meter here. You get 1.77 kilonewton here, 20 kilonewton here, 11.77 kilonewton here. The load is 10 kilonewtons here, and that's it. That is the solution that I want you to get. Is that clear? I hope you'll be able to solve this particular problem, and that brings me to the end of the moment distribution method as applied to beams and frames, beams and planar frames. Thank you very much. From next time onwards, I'm going to be starting off on matrix methods. Bye.